This, and the other learning resources in this course have been made possible by funding from the European Commission's Erasmus Plus program.
Presentation, voila. So today we're gonna do a talk about the presentation that I was actually going to present you on Tuesday. However, in order to allow you to get more familiar with the software, I have decided to switch the program a little bit and make sure that you can just practice it as much as possible. So CloudCompare, it's a free software. Well, free doesn't exist actually, but it's open source software, and you can, under normal circumstances, download it and install it for free with an open license. I'm running CloudCompare on a Windows computer and on a Mac computer, and apparently it also works with Linux. It has been a while that I've installed it myself on Linux, so in the previous version it worked very smoothly on Linux. But I don't have any recent experience with that. So it's originally developed as a PhD project of a French scholar. He's now very famous because the software itself is heavily used by many researchers and many companies. And originally it was developed to work with laser scan data for visualization and processing of very large point clouds. So when I started my bachelor, master, and even during my PhD, it was a very big important bottleneck to process large point clouds. So as soon as you go to point clouds with more points than, let's say, 2 million or 5 million points, many software packages were not able to handle that properly. For example, if you want to work with point clouds in AutoCAD Civil 3D, for example, that's still not very convenient to do. And on the other hand, there was software available like Leica Cyclone that I'm using with my Leica scanner, but also RealWorks for Trimble and what's the name? I think it's Faro Scene for the Faro scanners. But these software are also quite expensive. So actually, if you want to work with point clouds, with large point clouds, CloudCompare is actually a very good and very useful alternative. So originally it was for emergency mapping in collaboration with the Électricité de France in France, the national mapping, the national electricity company, for deformation monitoring. So especially if you look on the first days of commercial applications of laser scanning, you will find applications on the measurements of chemical constructions, like very big cylinders with a lot of pipes and stuff like that. And if you have a scan on T1 and you have a second scan on T2 or T0 and T1, you're actually able to measure potential deformations in your construction. So that is why CloudCompare was originally developed. But as the time goes on, there were many plugins written, many additional features were implemented in this software. So nowadays we can also use it for as-built documentation. So I will show you some examples of the scan that I took the day before yesterday for architectural modeling. Landslide monitoring is also a very cool application. We recently submitted a paper on land deformations in Switzerland, and we heavily used CloudCompare for the calculation of volumes of landslides and permafrost development. Hydrology, also a very interesting and cool application. If you're, for example, working in bathymetric applications, you will find tools like Kinsey or from QPS, very useful for the integration of bathymetric data, airborne laser scan data, motion sensor data. So these are purely hydrological or hydrographic applications. And also CloudCompare is very useful to visualize these points, process these points in terms of filtering, in terms of generating deliverables. And of course, what we are going to do here is work with CloudCompare for cultural heritage documentation, mainly in the framework of as-built documentation. So if you open CloudCompare, it looks like the pre-ribbon software in the pre-ribbon era that Arash was also referring to when we talked about AutoCAD a few days ago. So you will not find ribbons here. You find classical menu bars, classical buttons on the top of your screen. So here are your menu bars and several tools and options that you can access. A main viewer for the 3D view of your point clouds. And actually, you will not be able to show only point clouds, but also triangulated 3D models in your environment. This is the area where you will find a database. So all the point clouds, you can add one or multiple point clouds in the software. And this is the area where you can structure them. A list of properties of each and every point cloud in your database, a console that we will have a look at, and here some 3D view tools. So each and every tool will be discussed in this presentation. Actually, the interface itself, if I'm very honest, it looks very similar to the interface that you will find with QGIS. So this is actually the equivalent of your map view. This is actually the equivalent of your table of content, a console if you're working with scripting or you want to have a look on your processing parameters. Very useful to work with that. So if you measure a point cloud, just a geometrical representation of a point cloud results in a series of points in a 3D space, and each and every point is actually just a 1D or an OD, depends on how you see it, representation of the object. So there's no topological relation. You don't see any normals or any colors in that point cloud. So this is the normal hardcore raw data that you can acquire with laser scanning or with photogrammetry if you export your point clouds. And of course, in each and every point, so let's say that this is 15 million or 20 million points, each and every point can get a RGB value, so a color code assigned to each and every individual point, and that will allow you to distinct certain objects in your point cloud. It will, at least in your mind, by looking at the point cloud, it will give you some kind of a visual impression of the point clouds that makes it much more easier to interpret the different clouds. Then there is the possibility to calculate normals. So if you have a surface, so let's say we have a surface here and you have the surface covered by your laser scanner by several points, then what is actually happening with normal calculation is that it will calculate the direction opposite of the surface itself. So if this is my surface, I will calculate for each point the direction perpendicular to the surface. But the problem that you find here is that this is extremely slow to calculate. So if you have a huge set of individual points, what is actually happening, it has to find local neighborhoods. So it will, for each point, it will take a neighborhood of 10 points, 20 points, or it will take a triangulation of the neighborhoods. And then based on that triangulation, it will calculate a normal vector. So this is not very convenient and not very fast, but geometrically very sound. Another way of improve the visualization of your point clouds is working with shaders. So here's an EDL shader, and this is extremely fast. So even also in your own point cloud, you will find this a very useful feature. So some basic features that we will discuss today, that we will go into a little bit more detail in the coming days, is that we can use our CloudCompare for basic manipulations of our points. So we can load point clouds, we can merge point clouds. We will be able to perform interactive transformations of the point cloud. And I will show you outside my presentation why this is so incredibly important. We can work with manipulations, so scale, close, merge, several point clouds. Actually very similar as what we have seen in Agisoft Photoscan or Agisoft Metashape. Interactive segmentation. So we will have the option to segment our data based on predefined properties or manually defined properties. Subsampling, also very interesting. If you have a point cloud of 26 million points, this is a huge amount of data that you will find there. So in that case, it's more convenient to work with a reduced point cloud, a sampled point cloud, where you say, for example, okay, I want each point every centimeter or every 10 centimeters. And that will result in a huge data reduction. Cross sections and the calculation of distances, areas, volumes will be something that we will discuss. Point cloud registration, and of course also point cloud filtering. So before I go further, I would like to show you something here. So what I did the day before yesterday, I went on site and I took my laser scanner, or the laser scanner of my department, and I made some scannings of an historical artifact. So this is an old monastery in Lierde in Belgium, where I live. So I took several scans with a focus on this building here. This is the old brewery, apparently, and I took several scans of that building. Well, what you see here is just a view as if I am on the scanner itself. So I have a full 360 horizontally. I can view 360 degrees in this direction. But if I look down, you will see that I don't see anything. And the reason I don't see anything here is obviously because of the fact that I have a scanner, and the scanner cannot look downward because the scanner itself is on its way. So if I look at my scanning position, you see here a black spot, and this black spot is of course caused by the scanner itself. There are some other things that are very interesting and that I want to share with you in this point cloud. And I will go into the details about processing and about the interface and blah, blah, blah in just a few moments. Another thing that you see here in this point cloud is that it has a lot of dark areas, of areas where we don't have any data. And that is obviously because of the fact that if we look at the scanner, we can only measure what we see from the scanner. So there's no problem on measuring this surface and this surface, but everything that is behind that surface is obviously blocked by the surface in front of it. So we have to work with multiple scans in order to have a full coverage of our object of interest. Some other things that are interesting here to show you is if you look at the car, you see here the backlights of the car are not covered. That's obviously because of the fact that there is a reflecting surface, metal or silver colored surface that is highly reflectant. So these surfaces are not cannot be modeled properly. Also, you see that the glass window of the car is also just an open surface. So these areas cannot be measured using laser scanning. Something else that is extremely interesting to look at, we are using signals in the electromagnetic spectrum. This scanner is a C10 scanner, and if I'm correct, it uses the green light signal. So it's a green laser that is emitting. Green lasers have the characteristic that it can hold a huge amount of data. So never look in the laser while it is operational. But very interesting here to see is that, of course, the sun that is shining on top of us is also emitting the entire spectrum of, or a huge part of the electromagnetic spectrum, among others also the green light. And that is the reason that in many raw data sets, you will find these sparkles here. So this is actually erroneously measured data. Definitely erroneous measured data. These are just the signals coming from the sun in the exact same frequency, or in exact the same wavelength as the scanner. And these points are actually just measured erroneously. So they are detected. You can see in this case, the sun was pointing in this direction. So this is my direction of the sun. So if we look at this point cloud, you will see that the coordinate of the center of my projection, as I said yesterday, the center of my projection has coordinates 0, 0, 0 by default. So the X, Y, and Z coordinates are 0, 0, 0. And why is this so incredibly important? That is because if I take another scan, this other scan is also measured from a position 0, 0, 0. So if I disable my scan 3 in this case, and I look at scan 1, I see another point cloud just from another viewpoint. Here I've visualized my, my point cloud, and you will see just the same building. Well, I'm looking at the wrong direction here. The same building from another perspective. So I will go to my scanner. And I will say, okay, let's take a bubble view. So this is actually what I measured from the other scanning position. So you see that the relation between this scanner or this scanning position and the other scanning position is of course totally different in terms of orientation and in terms of positioning. So what we have to do here is actually merge these two point clouds. We have to filter them in order to get rid of all these erroneously measured artifacts, but we also have to register our point clouds, to merge our point clouds. And in a few days, I will discuss you how to do that. But in many cases, you will find things like this. Let me zoom in a little bit. These objects and these objects, these are targets. So with photogrammetry, we discussed about black and white targets. In laser scanning, you can also use black and white targets, but there are some other different targets as well that can be recognized automatically by the scanner. And I use these targets to do the automatic registration of my point clouds. And that will allow you to generate a spatially coherent view of your object. If I get out of this point clouds and I take the point clouds again, then you at the end you will see that all point clouds are nicely aligned. Unfortunately, I don't have a license for point cloud registration yet, so I had to do it manually. And I would like to share with you the results of that. So if I go here to this is, by the way, a point cloud's airborne laser scan data of the same area. I can improve the visibility by using this shader. So voila, this is the same area by airborne laser scan data. In the Flemish region, these data can be obtained for free. But what is very interesting is that if you have aligned all your point clouds together, you will actually end up with something that looks like this. So combination of airborne laser scan data, several terrestrial scans. And this is the result of 5 scans overlaid by the airborne laser scan data. And we have quite a nice coverage of the building. So the techniques behind it, the filtering of these data, these are all topics that will be discussed in the coming days. Just a small question. Is Mustafa available? Mustafa Kes Havarz. Okay. Well, let's then continue with the presentation itself. So one of the biggest advantages of CloudCompare is that it supports a large amount of file formats. So we will mainly use CloudCompare for the visualization and processing of point clouds. Just a little moment, because there's somebody getting into the waiting room all the time, and it's extremely annoying. Try this in the
He was Mustafa in the waiting room.
Yeah, but he's joining 3 times, and I receive a lot of messages about it. So I hope there are no technical issues for him. And now I see him in the list of participants. Mustafa? Okay, let's...
Yes, I joined it. Thank you.
Okay, perfect. Because I see you here in the list joining us for 3 times now. So I hope everything is okay.
Yes, it's okay. Thank you.
Wonderful. Wonderful. So with CloudCompare, we are able to load many file formats. So we have our classical ASCII-based file formats. In the chat, I just sent you also a little text file that was not included originally in the demo data for this session. So that's why I uploaded in the Zoom function, just to give you an idea on how to load ASCII-based data. And most of the times we will be working with LAS data. So this is standard data for laser scanning point clouds, especially when you work with airborne laser scan data. These are most of the time delivered in the LAS format or in the compressed LAZ format. This is a binary-based format, but very well documented by the American Society for Remote Sensing. In Metashape, we also saw very briefly the option to export to E57. Also a binary format that has the ability not only to incorporate your point cloud, but also acquisition parameters. It's also very useful. And then some other laser scan formats. Triangular meshes. So if you have generated your meshes, for example, in Metashape, you will also have the option to load these triangular meshes, so 3D models in CloudCompare. And with the latest version of CloudCompare, it also supports the textures that are included in the BLI file or the OBJ file. So if you have a cloud, if you have a point cloud or a 3D model generated, you can use these models in CloudCompare for further processing. And then some other formats. So if you work with Bundler as an open source software for structure from motion, you can use Bundler data in CloudCompare. The original PhotoScan projects can be imported in CloudCompare, and there are some other cut and even spatial data that you can use here. Loading these data is actually quite simple. So what I can do, I can go to an empty CloudCompare project. I'm loading CloudCompare now, and then I can go to open, and I will go to my projects, demo 4. Actually now you can also in the chat you will find this gcp_source.txt. That is the file that I'm going to load. So if you want to join me, please go to the chat functionality and take this file. It's also uploaded in the on the server, by the way. So I can press gcp_source.txt, and then I get into this interface, this tiny interface that will allow me to set the data, to set the different fields for ASCII-based data. So if I take the original file and I open it in my notepad, I will see a point ID, so a label. This is actually just a label. I have an X coordinate, a Y coordinate, and a Z coordinate. And the useful thing about this is this can actually be ground control points that you measured with a GPS or with a total station. So if you just make it a simple list, potentially even in Excel, You can just make your files in Excel, put them in a TXT file or in a CSV file, and you can import them in CloudCompare. What is important here is that you have the ability to set your different fields. So with since version 2.10, you have the option to set a label, which is very useful. But you can also set your X, Y, Z coordinates, the different normals, colors within the range of 2 to 255, or floating points from 1 to 0, grayscale data, and optionally also a scalar field. So for example, if you have a weight that you want to give to a point, or an additional field, you can use that as a numerical scalar field in this case. But here I have my label. I have an X coordinate, a Y coordinate, a Z coordinate. I know that my separator is a comma. If that is not the case, I can change it here. And I will not skip any lines, so I can just press apply. Because of the fact that the points that I have shared with you, so let me open them again. The points that I shared with you are in UTM. So this is UTM 35 North. It's a Greek series of Greek coordinates in this case of Eleusis. And that is why that these coordinates are rather large. So you will see that the X coordinate is in 459,523 and 24 and blah, blah, blah. So these are quite large coordinates. And CloudCompare, if you want to load these kinds of points, it will ask you to perform a global shift. And the global shift, what it actually does here is say, okay, you have your point clouds that are georeferenced in an absolute system. I have no idea what that system might be, but what it will actually do is try to take these coordinates, apply a temporary shift, a translation. This is actually just a translation in this case, in order to have the center of gravity of your object in the in your 0, 0, 0 coordinates. And that will allow you to speed up the process. It will increase in performance. If you do any modifications of the file in CloudCompare, the inverse of that transformation is taken. So you will not have to worry about, okay, I'm having a transformation here. No, it's just a temporary shift. As soon as you close your project or save your project, export your project, this shift is reversed and you will have your original coordinate reference system. So I will apply yes to all. And the result of that is that I have here my points, 4 points with a label, and they are positioned in 3D. So this is perfect. And that is how you can load ASCII-based point clouds. So voila, assign your fields and blah, blah, blah. We can also do the same for the data that you most probably found in your in the demo folder. So I have here tls_eleusis.las. So this is the standard for airborne laser scan data. I will not load them here. I will actually just take them and drop them in my CloudCompare environment, because I will show you something very interesting. But before I show that, this is the import interface. So each and every point in your LES file can include several fields. So an RGB value, classification, number of returns, blah, 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 blah. We can even set additional fields, some other meta information. We will not consider that here. I will just say apply. And then I get the same message as the message that I received for my points. Well, I will be honest with you. The points are not actually ground control points. They're just extracted from the original point cloud. So here I have several options. If I press here, I can say, okay, let me take the suggested, and then it will just take the boundary of my the imported point cloud, and it will calculate the center of gravity of that point, and it will just rotate, just translate everything. But I also have the option to take the last input, and in that case, it will take the transformation that has been calculated for these 4 points. And that's what I want in this case, and that's what you want in many cases. So if you have an instance of CloudCompare open and you already applied such a transformation, it's always a good idea to use last input here. So I press yes, and now I'm opening 26 million points that are loaded in my point cloud. Voila, and this is the result. So this is exactly where I took my points, so this is good. Voila. And in the next few slides, we will work with this point cloud. So the ability to work with LAS data, but if you have like the E57 data sets, it's the same. You can just drag and drop them, or you can use the open functionality. Explain to you about this, and then we have our point cloud. So something about basic manipulations. If you want to modify the point or to change your perspective on the point cloud itself, it is, especially in the beginning, if you're not familiar with 3D modeling software, it's very convenient to use your mouse for that. If you use your mouse, or if you just want to use your touchpad for your touchpad for it, the modification or the manipulation of your view is quite intuitive, especially if you're familiar with AutoCAD or with SketchUp or other 3D software. So camera rotation, let me go here. Camera rotation is just a matter of clicking your left mouse and then rotate your view by moving your mouse. You can also pan by right-clicking, and you can zoom by scrolling towards your point cloud or scrolling towards your point cloud. Also, you can use the buttons for zooming in and zooming out, pressing the plus button. And instead of, if you want to zoom out, you cannot press the minus button, but you will have to press the equal button. If you're working on a Mac, the modifications are very similar. One press is for a rotation. Two presses are for panning on your touchpad, and zooming is just sliding over your touchpad. If you're in a situation like this, so I've zoomed in a lot, I lost a lot of information, so it's very difficult to interpret my point. It might be very convenient to use here the default point size. So you can improve the point size. Might take a while. You can improve your point, you increase your point size, or you can decrease your point size. And now I'm back in my original situation. So we have our point in our viewer. Actually, I have 2 point clouds in my viewer at the moment. Let's have a look at the interface. So if I press here, by the way, are you still with me on this one? If there's anything unclear, please feel free to interrupt me.
Okay.
If you press here on the TLS underscore Ellipsis, so the huge point cloud, it will give you access to the properties of that point cloud. And there's some very interesting parameters that you will find here. So first of all, the name and the ability to visualize or devisualize your point cloud. Same actually holds if you press just here in the database viewer. You can also hide and visualize your point cloud. You get some geometrical information about the dimensions of your point cloud. So you have here an XYZ dimension. So I have a point cloud. If I take the bounding box is actually here the green area that I have around my my point cloud, and it has a dimension of almost 90 by 90 meters and a height of almost 20 meters, 19 meters. This is the parameter of the this is the parameter of the global shift, so the value that we used while loading the point cloud. And this is the coordinates, the local coordinates, so not the absolute coordinate, but the local coordinate of the center of our box. So it's actually just the balance of these box dimensions. We have some information about the number of points. So indeed, we have 26,340,000 6,000 blah, blah, blah points in our point cloud. And here we have some transformation parameters and some metadata available. Another interesting parameter that is not very relevant for now, but that will be relevant for later, is here the color visualization. So in this case, we only have the option to say, okay, I don't want any colors. So then I just have a series of points that are very difficult to interpret. Or I can take the RGB value. So this is the true color composite that I have here. You can, if we calculate distances, so cloud to cloud distances or cloud to mesh distances, or if you want to calculate a certain scalar field on your point cloud, you can actually say here in a few slides, okay, I want to measure or I want to calculate to visualize this certain scalar field. I will discuss that later on. These tools are also very interesting. So we have the ability to take a top view of our point cloud, a side view of our top cloud, another side view, a bottom view. So this is very similar to what you will find in AutoCAD. And the orientation of these viewers here that you will find are also related to the axis that you will find here in this case. So here you will see that our blue axis is not very clear, so let me zoom in a little bit. The blue axis here is my Z direction, my green axis is my Y direction, and my red axis is my X direction. And that actually allows you to get a better understanding of the orientation of your point cloud. Obviously, this is only relevant if you have a reference point cloud or if you have settled your point cloud correctly. And that actually brings me to this slide. Voila, to this slide and to the next coming slide. So if I have a randomly oriented point cloud, I will just take one from here, for example. No. Let me find a random point cloud. I will take this one. So if this is my point cloud, and I want, for example, to make an architectural map of the frontal side of this point cloud, of this fountain in this case, you have several options. So in that case, it is preferred to have my blue axis, so my Z axis pointing towards me, so pointing in this direction. And in that case, I actually want to rotate my point cloud. So I select my point cloud in the database manager. Then I go to rotate and translate, or translate, rotate. And then here I have the option to set my rotation angles. So in this case here, I can rotate on all my three main axes. Or you can say, okay, I only want to rotate around my Z axis. So now I can only rotate using my left button. If I set it in my X, Y, Z direction, I can just rotate in all directions. What you see here, TX, TY, and TZ, is actually the ability to translate your point cloud. So now I can translate it in all three directions. If I say, for example, okay, I only want to translate in the X direction, now you see I can go up and down, but it will only change my orientation in the Z direction. Very useful is this function. So imagine the situation that you have made a 3D model. And that 3D model, you used a ruler or you used some kind of a reference distance to at least to scale your 3D model, but you want to have, you're not able to set the orientation of your model correctly. In that case, you can use the level tool, and this level tool will actually allow you to pick 3 points, and based on these 3 points, it will set your horizontal plane of the object of study. So let me demonstrate that. If I go back to this point cloud and I just randomly orient my, my point cloud. So this is a random orientation and I press OK. Now if I look at my, my top view, if I take it like this, now my orientation of my X, Y, and Z axis are totally random. So if I take a top view, I have something like this. So let's use this level function to say, okay, here, this area will be my flat surface. I go to Tools, I press Level, and now I will have to pick 3 points on the floor plane. So let's say pick 1, pick 2, and pick 3. And now it will orient my my object in the in this horizontal plane. So now my Z direction is pointing towards me. If you want to rotate this point cloud, then afterwards you can just say, okay, let's rotate around the Z axis, and we can just rotate the fountain a little bit, maybe even translate it a little bit. And voila, we can use it in a later stage for DEM processing, or even to make some kind of a pseudo orthophoto out of it. So this is a very useful tool if you want to work with locally oriented or locally transformed point clouds in CloudCompare, the plane level. But please never use it in case you work with terrestrial laser scanning where you have set your vertical axis. So if you have used the tribug to set your vertical axis, don't use this tool in that case, because in that case you will just rotate your resulting point cloud in all directions, and you will lose that very useful information. So only use it in case of locally, totally locally oriented 3D point clouds. A few more slides before we will have a little break, and that's actually I think it's best to have this as the last slide before the break. That's a segmentation tool. So the first thing that you can do to say, okay, I have a very large point cloud, but I'm only interested in a small portion of the area. So for example, I have here this archaeological site, and I'm only interested, for example, in the base of this area. In that case, you want to cut out all the rest of the point clouds. For that, you can use the segment tool. If you want to do that, you press here the point clouds. You can go to your scissors. So here are the scissors, and then you can make a polygon 1, 2, 3, 4, for example. To finish a polygon, you can press right click, and then you can say, okay, I want all the points inside my point cloud, or I want to retain all the points outside, inside my my polygon or outside my polygon. So in this case, I want to segment everything that is inside my polygon, so I press inside. Maybe if I look at my point cloud like this, I want to get rid of these little artifacts that are here. So this white area. And in that case, I can unpause for the second session of my segmentation and just make a boundary around this artifact, right click to close my polygon and press outside. And in that case, this artifact will be gone. If I'm happy with this segmentation, I can just accept, confirm segmentation. And now you will see here 2 point clouds. The one that I want, so this is my segmented point cloud, and the points that I have removed out of my segmentation. So this is just everything that is outside. This is the part of the first segmentation, and this is part of the second segmentation, but that's all merged into the point cloud entitled cloud.remaining. And this is my, my final result. So this is quite useful for manual filtering, but also if you have a very large area covered by your point clouds, you can just take small samples of large point clouds. Well, since we are talking about segmentation, I will just explain you a little bit more about data reduction as well. So if you say, okay, I have this area, I'm very interested in that area, but still I have 13 million points, and the processing goes very slow. So it's not very convenient to work in the software, and I don't need all these data because
Professor.
yeah.
I have one question.
Yeah, sure.
That point 2 is outside of the box. Is something to do with this point?
Ah, this point. That was from another point cloud. So this this point, the point #2 that you that's another point cloud.
Ah, okay. Okay. Thank you.
Yeah, thank you for your interesting question. So this bounding box is only valid for the point cloud that is currently selected. If I select my second point cloud, visualize my second point cloud and select it as well, then I will see two bounding boxes, one for the interior for our segmented point cloud, and the other one for the point cloud that was outside my segment. So in this case, I'm just interested in this portion. I still have 12.6 million points. Yeah, voila, 12.6 million points. That's a huge oversampling. I don't need all this information. I just want to have a point cloud where, let's say, I have 1 point every centimeter, for example. You can do that in different ways. I select my point cloud here, so the segmented point cloud, and then you can press here subsample a point cloud. This is a very interesting tool if you want to do some data reduction. So if you say here sampling point cloud, you can first decide on a method. You can say, okay, I want an octree-based segmentation. What is actually happening in that case is that it will make an octree. So an octree is a 3D quadtree, and a quadtree is actually just a series of squares. There's a very interesting, a very good visualization of octrees. Point clouds, and that's frequently the rabbits. You will find the point cloud of a rabbit. Voila, here it is. So what's actually happening here in this octree structure is that the software will make a lot of cubes, and it will say, okay, there's a point inside this cube, so let's take that cube and make other cubes. So each cube is then divided into 8 new cubes, and it will say, okay, did I find in each of these 8 points, did I find another point? Yeah, I found another point, so let's divide it. So actually you will end up with something like this, where you say, okay, I have a first level, there's a point inside, then I have a second level, there's a point inside, there's a third level, etc., etc. So it's a way of optimizing your points. So there are many examples of that, and that's also what's happening here behind the scenes. And then you can say, okay, I want that many subdivisions of my my cubes. Most of the time, I don't use that. I say, okay, I take a random sample, and random samples. In that case, you can say, okay, from these 12,619 points, please give me 2.5 million points. Let me count if I have enough zeros. So 2.5 million points, and then you can press OK, and it will randomly take 2.5 million points out of your original point clouds. So here I see indeed 2.5 million points, and I still have the overall geometry of my site. Be very careful with this random selection, because if the distribution, the spatial distribution, is not equal in your point cloud, and that is definitely the case when you're working with terrestrial laser scanning, then this technique will result in very low density points far away from your scanner. And why is that? Remember that if we go back to the point clouds, I don't have it here anymore. But if you have a scanner, you will set an angular value, an angular increment, and it will say, okay, measure a point here, measure a point here, measure a point here, measure a point here, measure a point here. It also results in the fact that the further you go away, the larger the distance between two consecutive scan lines. So we have a very high density here in this circle. This is actually where one of the scannings has been taken place. A very high density, and we have a very low density as a function of the distance of the scanning position itself. So that means that if we say, okay, we take a random sample of points, 2.5 million, 5 million points, that will actually retain this irregular point density in our point cloud. So I will not use that one. I will go back to my original 12.6 or 12.7 million points. I will go back to subsampling and I will say, okay, I don't want to have a random selection. I will take space. And in that case, I can set this parameter here, minimum space between points. And here I can say, okay, I want, for example, 1 point every 1 centimeter. And if there are between 2 points, if the distance is less than 1 centimeter, it will eliminate a point. If it's more than 1 centimeter, it will retain the point. And it will give you a more equal distribution of your point clouds. Obviously, it will also take a little bit longer to calculate this, this subsample, because it will have to measure a lot of relations between different points. But eventually, we have a point cloud with a very nicely equal distribution, or the distribution is obviously nicer than the distribution that we had with our 2.5 million points. But in this case, our the number of points is still quite high, 10 million points. So you can say, okay, maybe I want to increase the distance a little bit, but be careful with that you don't lose too much detail in your original point cloud. What you can do then, just as an illustration, here I have my my subsample point, and now I'm in the last slide for the break. So this slide, subsampling. What you can do here is you can go to Tools, then you go to Other, Compute Geometric Features. If you click here, you can see a lot of parameters, a lot of geometrical parameters that you can calculate for that selected point cloud. So a surface roughness will give you the roughness of the local topography, the curvature, so it's the to detect convex or concave surface deformations. Actually, if you're more mathematical, if you have a little mathematical background, the slope is the first derivative of your surface, and the curvature is the second derivative of your surface. So it's actually this is actually the slope of the slope. But in this case, we will look at the density, the point density. So number of neighbors per surface area. So let's say, okay, I want to know how many points are in every 10 centimeters of my point. I can press OK. And then it will calculate the number of points. It might take a while. I hope not. It should go fast enough. And then under normal circumstances, you will get something like this. So what it calculates is actually a first scalar field. And I hope it will stay awake. A first scalar field where for each point, I calculate the number of points within 10 centimeters around it. So for each point, I say, okay, I have a point here. Let's make a sphere of 10 centimeters with a radius of 10 centimeters. How many points are included that sphere? And you can use that as some kind of a quality measure to say something about the density of your point cloud. My computer starts blowing a lot, so I'm a little bit afraid. It's still calculating. Voila. So this is the density of my point cloud, and I will show you in a little bit more detail how to interpret these data and how to use these kinds of values. But for now, I would propose to have a little break. Let's say again 10 minutes. It is, if I go to the presentation, close it. It is now 5:10. So let's meet again at 5:20 Central European time, unless you have any questions so far. Do you have any questions? Then let's meet in voilà. Here's a question. I assume that it's easy to work with CloudCompare until this moment. Yeah, that's definitely correct. But what about TLS files? How did you create it? Yeah, the creation itself was done by the laser scanner. So that's what I did the day before yesterday, and I used Cyclone to do processing. So software that comes with the laser scanner. I assume that Michele, who will do the guest lecture on Monday, that he will tell you more about this software. So the step from acquiring the data to having your point cloud is something that I will not cover in Cyclone, but I think we will cover that on Wednesday or Thursday. I will show you how to combine different separated TLS files. And also I will show you the cleaning of the data, registration of the data, and also visualization in online environments. So something similar that we did with the panoramic viewers, you will also be able to generate something like this. So here we are looking at many millions of points. It's just pre-processed data, combination of the airborne laser scan data, terrestrial laser scan data in a web-based viewer. So that's things that we will cover in the coming days. Did that? Okay. Thank you for confirming. Well, let's meet again in 10 minutes.
Okay.
Zoom recording. So the first one is we go to edit, multiply scale, and then you can set in certain directions, in multiple directions actually, a scale function. This is only relevant if you're working with local coordinates. If you say, okay, I have an object and I want, for example, an object where I have all my measurement in inches or in feet, and I want to convert them to a metric, to the metrical system, you can apply a scale factor here. So just set your own value here. But of course, I will definitely not recommend that if you're working in a metric system already. So just for your information, know that that is possible. Another very useful thing is that, for example, let me remove this point cloud. If I want to do something with these data, so these two point clouds, I will select them both using the control button. It is a very good idea before manipulating the point cloud to make a clone, to make a copy of this point cloud. So select them, press clone, and you will find two identical point clouds. So if by one reason or another something goes wrong with your data processing, you can always go back to a previous instance of the point cloud itself. I made a segmentation here. So I have my outside area and I have my inside area. If I say, no, I don't want to do that after all, or I have multiple scans from multiple scanning positions, you can select the different scans and press fuse or merge multiple clouds. It will ask you, do you want to generate a scalar field with the original cloud index? That will actually mean that the outer area will get an index 1 and the inner index again will get a an index 2 or vice versa. So let's select that one. And now I have 2 point clouds here. So here these are merged. And in that I have a new scalar field, and the scalar field, it will say, okay, I have a field, a point ID 1 and a point ID 2 that is referring to the different original point clouds. And if I want to go back to my RGB values, then I can just click here, colors RGB. So this is quite useful. The next thing, making sections, and this is something very interesting in more advanced point cloud analysis. So I select my point cloud, and then I go to segment, here cross section. And then you can say, okay, I want to make a cross section like this in this direction. So you can just rotate your bounding box. Use the handles here to increase or decrease the dimension of your boundary. And then you can say, okay, I want a section like this, for example. Voila. In this screen that has appeared while making the cross sections, you can define the parameters of your cross section. So you can actually see now in my X direction, so the red axis, it's decreasing and increasing. The same holds for my Z value and for my Y value. And if I'm fine with this cross section, I can actually press here, segment, export section as a new point cloud, and I will have a new point cloud. Voilà, here you see it. And this point cloud only contains the points that are inside my current bounding box. So it's actually a way to modify the bounding box. If you want to build multiple sections, you can press here. And you can say, okay, in my green direction, so in my Y direction, I want to have as many segments as possible with an interval of 25 meters. And if I press OK, it will make, in this case, 3 sections, and the distance from this section to this section is 25 meters. And that's quite useful as well. Voila, here's my, disable the original point cloud, my first section, my second section, and my third section. Right click, delete, and now my sections are gone again. Same here. I can also decide to delete this cross section. Another very interesting thing you can do using the segment tool. So let me go back to my correctly oriented bounding box, is the option to work with contours. So if you press here, you can actually make a line, a polyline, along your section. So let me remake my section here and make a section here. If I want to make a line on this cross section, you press here, and you can say, okay, I want a section in the X direction. So now it will make a section as I have it here. If I just want it in the other direction, I can select my my axis here. A maximum edge length, if there is a certain distance between 2 points that is larger than this given value, then it will make a new line. So you can actually make a multi-polyline in this case. So let me press OK, and now it will draw a line on the projection of this section. Might take a while, but here it is. Okay, let me go out of here. Let me close this. Why is this so incredibly interesting? Well, if I go to that line, so here it is, my contour line, you can actually select that point. You can select that point, and if you go to save, you can save your point cloud in several formats. So a shape entity, so an SHP, a shape file, but also with DXF. So this is quite useful also for further processing, because it's a very rough line that I generated here. If I export it to a DXF, I can import it in AutoCAD and use it for further data processing. By the way, I didn't tell you that for now. If I have here my my section, not this one, but for example, the segmented area, what I can also do is just say here, click save, and then I can say in my project, okay, Eleusis segmented, and I will have the option to generate a new LAS file or a new PLI or E57 file, only containing the points that are inside this point cloud. So that's also quite useful. If you did some data processing, of course, you should be able to save your work. And you can do that by just clicking on the point cloud, press save, and make a new point file out of it. If you want to save everything, you can just select everything, pardon, press save, and then you have the ability to generate or to save it as a CloudCompare entities. If you do that, it will save the project as it is at the moment. So it means that if you open that bin file that is generated in CloudCompare again, that you will have your several instances here in your database available again in your data viewer. So it's also a very nice and interesting way to save your work. So these scalar fields, I already mentioned it a couple of times. We have per point, we have an XYZ value. Optionally, we have a color, an RGB value assigned to it. And we can assign many scalar fields to each and every point. So this is, for example, a screenshot where distances are calculated, apparently here in millimeters. So imagine the situation that you're working with an architect. The architect makes a model of a construction. You make an as-built 3D point cloud, and then you need the option to compare your as-built point cloud with the design coming from the architect or from the engineer. And CloudCompare allows you to do these calculations and assign the distance from each point to a 3D model as a scalar field. And these scalar fields will also, the visualization of these scalar fields is also facilitated by the ability to modify your color range. That's something that is shown here. I will also demonstrate it. No, I will not demonstrate it here yet. If you go, wait, I merged. It was not merged here. You remove this point clouds and merge these two again. All points. I want to have this scalar field assigned to it. So now I have a scalar field, a very simple one. It only contains a 1 or a 2. I can go down, and then here I can play with the visualization. So now all the blue points are visible. Oh, I hope that CloudCompare's, yeah, it's blocked. It's gone. Maybe I have a scalar field here. No, CloudCompare is blocked. But this actually allows you to say, okay, I am only interested in a small portion of my my color field. Please gray out all the points that are outside this interval, and you can use here these tools, displayed and saturated, to modify your scalar fields. It is also possible to modify the scale bar itself, but I've never used that. I always use the default colors. But please know that if you're more into graphics, or you want to make nice or improved interpretations of these point clouds, that you can use your color scale as well. if you have your scalar fields, it's obvious that you can also do some calculations on them. So if you have a scalar field that, for example, gives you the incidence angle of each point related to a base surface, that's something that's frequently done as a parameter for point cloud filtering, automated point cloud filtering. Assign a weight to it's based on the incidence angle of the scanner, and then you need some goniometric functions. These are available, and you can also use the scalar field to do some filtering on it. Let me try something out. If I take, for example, this fountain that was already put in a plane, what I can do in that case is say, okay, I have a plane here. Let me calculate the best fitting plane. So I go to mesh and I say Delaunay 2.5D best fitting plane. Voila, here's my, no, this is not my plane. Plane fit, I'm sorry, plane and fit. Voila, so this is my best fitting plane. And what you can do then, I will go in a little bit more detail in a few slides. This is just to have some meaningful scalar field. I can compute the distances from each and every point to this plane, assign it as a scalar field to my point. So voila, the color scale that you see here is actually the distance from each point to the plane. And then what you see here in this slide is that you can say, okay, I have a distance, the distances have a certain distribution, so you can show histogram, and that will give you a visualization of your of the distribution of your distances, which is actually quite interesting because using these distances you can already eliminate some of the far outliers, and you can use the same scalar field here also to say, okay, I'm only interested in the points that are situated here under this plane, for example. Take nice coloring, and then you have the distances, the color expressed as a distance function to your plane. So you can use that as a coloring function. But even more important is the fact that you can also say, okay, I want to eliminate all the points that are too far away from this point or from this plane, and then you can, if my zoom allows me, you can say here filter points by value, and here you can say, okay, let's take, for example, all the values that have that range from -60 to 0 exports, and then we filtered out all the points that are further away than minus 60 centimeters in this case. So all the negative values are extracted by doing that. Another interesting thing to use filtering is the, when it comes to data cleaning, and we will go into a little bit more detail on Wednesday or Thursday, is of course using the segment tool for filtering. So if you have a point cloud that contains a lot of noisy data, you can use the segment tool to manually filter the data. I will go back to the demo data of Eleusis. Not this one, but this one. So there was some noisy data, for example, here, these white lines, they're just artifacts from the scanner itself, scanning the sun actually. So you can use here segment, make a polygon around these areas. Voila, right click to close the polygon, use only outside points. And then in this case, I filtered out these lines. So it's now, they're now gone. And I can save my point as Eleusis _ clean data, for example. Another very useful tool that I will not demonstrate is the connected component extraction. It will actually make clusters of several points. And if a cluster has less than a certain amount of points, you can just eliminate them. Statistical outlier removal is something that we will discuss in another presentation. And then, of course, the use with scalar fields. But that's also for the next days to come. If you have made a 3D model or a point cloud of a circular or cylindrical structure, there's an option to use unrolling functionality to actually unroll your cylinders. So, for example, you made a 3D model of a column in a church or a mosque or anything like that. A cylindrical shape of a point cloud, then you can use unrolling to make a projection, a cylindrical of a decylinderized projection of that object. Can be quite interesting for object interpretation. And this is definitely something that we have to discuss during the publication, for the publication of the data, the possibility to make rasters and contour lines. I will go here to my point cloud again. So let me take the pseudo-cleaned data in a top view. With my point cloud selected, I can go to Tools, Projection. Here's this unroll function that you will use for your cylindrical data, which I will now click on rasterize. And then for this point cloud, you can set your step size. The step size is the resolution of your DEM. So let's put it on 50 centimeters, for example, just to give you a rough idea. No, 10 centimeters. What will I use as an active layer? You can set your height. So that's actually just the Z value of each and every point. Or you can use the RGB. So you will have some kind of a pseudo orthophoto. I can do that here. A projection direction, as in Agisoft. Do you want to project in the Z direction, the default value, or in the X and the Y direction? The height. So if you have multiple points per cell, what will I take? Will I take the minimum value, the maximum value, or just the average? And if there are gaps in my data, how will I deal with, sorry, that's here. If I have empty cells, how will I deal with that? Will I interpolate it, leave them empty, use the minimum height, average height, or anything like that? So I will just set this to 0 for the time being. No, I will not use 0, leave empty. Just leave them empty for now. And now here I have a DEM. If I press raster, I can export this as a geotiff, and this geotiff is then referenced. It's not referenced in terms of it, the coordinate reference system is not assigned to this raster, but it knows its translation, rotation, and scaling parameters. And in that case, I can export it to and export it from CloudCompare and use it for further data processing in QGIS. The option to calculate a hill shade, also quite interesting. The orthophoto function, or pseudo orthophoto function, so RGB. Now I have an orthophoto with a resolution of 10 centimeters. And here the option to calculate contour lines. So I take my start value. So the start value is preferably the lowest value of my box. So I will take 10 here. Is that correct? 10. Nee. I will take 0 with a step size of 1 meter. And now I will generate of my height, of course. Voila, and it now generated contour lines. It's not that clearly visible, but it generated some contour lines of my based on my point cloud. And these lines, if I press export. I have my contour lines here in my database, and these contour lines can then be exported to DXF or to shape files that can be used in AutoCAD or in QGIS or ArcMap, wherever you want to use them. So actually this rasterized screen is quite useful to work with, to prepare your deliverables based on point clouds. So definitely something that you might want to use. Estimation of volumes. Important to mention here that the volumes are calculated in 2.5D. So if we go here, let's close this screen and go to volume, compute 2.5D volume. It actually projects all the points to a certain reference surface in a vertical direction. So if I want to calculate the area, for example, that is under the site up to a reference level of, let's say, 10 meters, for example, then it will just calculate all the distances from each point to that reference plane, and it will multiply it by the resolution of your raster, and that will end up, of course, with a volume. If you have two surfaces, it will also calculate the vertical distances from one surface to another, or surface from one surface to a point cloud, and it will extract the 2.5D volume based on these on this comparison, on this analysis. And more advanced tools. This is definitely something that I use a lot. It's the cloud-to-cloud distance. Also a very interesting parameter if you want to do filtering on point clouds, but mainly to work with deformation measurements. The main idea that we have here, this cloud-to-cloud distance, is that you have a point cloud. Obviously, you have a point cloud. So let me consider this point cloud here. Let me take a random extraction of this point cloud. Random, and let's say we take 1 million points. And then let's assume that this point cloud has been taken a few years after the first data acquisition has taken place. So I will just a moment. So here I have 2 point clouds, 1 point cloud here. This is my subsample. Let's consider this as my my second point cloud, and this is my latest point cloud. So what you can do now is, if you select these 2 point clouds and you want to calculate the distance from one point cloud to another point cloud, I will devisualize this one. You can select the 2 clouds and then press here on compute cloud-to-cloud distances. If you press here, you say, okay, what's my reference and what is my compared? So for what data, on what point cloud will I project my distances? In this case, I will use subsampled. My reference is segmented. You can swap it if you want to reverse those two. And then it will say, okay, for these 2 point clouds, you can define a maximum distance. So all the distances that are further away than a certain predefined value will be excluded from the analysis. I will not use it in that case, or in this case. You can say, I don't want just one distance, but I want to have the distance in X, Y, and Z. That is possible. And there are some other parameters that I will not discuss here. It's on the orientation of your reference surface. So let's just click compute. And what it will do now is that it will take 1 point from the point cloud, and it will calculate the distance to the nearest point in the opposite point cloud. And this distance is then assigned to the compared point in the point cloud here. And you can use these values to get an idea about the distance or the distortion between 2 points. But also locally, you can use these deformations to say, okay, there has been a local deformation on my archaeological site, or if I have a structure and there has been some erosion taken place, some chemical erosion taken place, then you can use these kinds of analysis to say something about the quantity of these processes. While it's calculating, I will continue my discussion on this one, because the problem that you will have is that if you take 1 point from 1 point cloud and you compare it to the closest point in the other point cloud, that this distance is by default always positive, because the distance just the distance in 3D is always positive. You cannot go in the opposite direction. But that will also depend, the quality or the results will also heavily depend on the resolution of your data. If, for example, you have two identical surfaces, exactly identical surfaces, but there has been a little translation of the scanning orientation, then you will end up with a result that is, of course, in the most ideal situation, or in the maximum situation, half the resolution of your reference point cloud. And that's not very convenient. And that's why in most cases it's more convenient to use a cloud to mesh distance. I always briefly demonstrated that to you. A cloud to mesh distance will not consider 2 point clouds, but it will take 1 point cloud and it will compare that point cloud with a surface. And the surface, you can generate surfaces in CloudCompare only in 2.5D, but this can also be a surface that you generated in Agisoft, for example. So imagine the situation, last year you went to an archaeological site, you made some photos, made a 3D surface of that archaeological site and of a construction that you find there. And then this year you go back to that site, you make another 3D model of the same artifact. They are properly referenced, so they are in the same coordinate reference system. What you can do then is take your previous model from last year, take it in, or load it in CloudCompare, take your point cloud that you extracted this year, and then you can use this cloud to mesh distances as a more rigid comparison of the two features. Because in that case, if you have a surface, then I know this is my backside of the surface, this is my front of the surface. So if I have a point here or a point here, in this case, I have a positive distance. In this case, I have a negative distance. So I can say something about not only the quantity of my deviation, the same as I would calculate in cloud-to-cloud distance, but also in the direction of my change. And that's why it is more accurate and more robust than a cloud-to-cloud comparison. If you have these distances, and yeah, voila, it's ready here. So let's press OK and close this one. So what I see here is the absolute distance of each point to its closest counterpart between the subsamples that I manually transformed a little bit towards the original point cloud. If I take this point cloud and I look at the distribution of my distances, and here are my distances. You see that all the distances are absolute. They have a positive magnitude. And apparently I performed a translation of, let's say, 2 point something meters. So they're all 2 point something meters below the original surface. And you clearly see here the distribution of it. Very peaked towards the maximum, very peak distribution that I have here. If I go a little bit up in my console, because I missed that, in this case here, this is also very interesting if you want to use these distances in a report. This is the mean distance and the standard deviation of your distance. So if you have two surfaces, for example, and you say, okay, I have two surfaces, I want to compare them. Is the distance between the two surfaces or the 2 point clouds, is it significant? You can actually use these data, the mean distance and the standard deviation of the distance, to tell you, to give you an idea about the significance of a change. If the mean distance and the standard deviation, if you relate it to the resolution of your data, you can use simple statistical inference to say it's significant or not. So I have here my histogram. Voila, my histogram. And if I say, okay, I want to use all the points that are, let's say, further away from my original point cloud than 1.6, then I can visualize that here in my histogram, remind me of 1.6. And then here I can say, okay, let's take all the points that are within a range of 1.6 to the maximum. So this is the maximum and here was the minimum of the range. And I can split it. Then I have 2 point clouds inside this range or outside this range, or I can just take the export. And then here I have all the points. Go back to my histogram, all the points that are in the range of 1.6 to the maximum of my distribution meters away from my original point cloud. And that's what you can do here by using the histogram and the range of the scalar fields. So that's very convenient and very useful. A more advanced way of calculating distances is the M3C2 method. It's properly documented here in a very interesting paper, and it will use not only the vertical distance from a point to a point or a point of a surface, but it will actually use some kind of a cylinder, and within the cylinder it will also incorporate the normal direction of each and every point. So this is more for advanced deformation measurements that you can use. This is a topic that we will discuss also on Wednesday or Thursday. So the registration of multiple points. I prepared a very nice data set of NavPlio for that. So that's data that we acquired in 2017. That we were in NavPlio with a Leica C10 laser scanner. There were several scans made. And I will ask you to experiment with the registration of these data using CloudCompare. So multiple options that you have here. You do just a rough registration, and then we can do a closest point analysis. That will be discussed in one of the coming days. Point cloud classification. So the ability to classify points. If you have a point cloud without any classifiers assigned to it, so in this case it's for geomorphological classification, then you can say based on the neighborhood of a certain point series, you can say, okay, it's a rock, it's water, it's gravel, or vegetation. More commonly used point cloud visualization is applied in airborne laser scan data. I already discussed that yesterday with you, where you have a point cloud of the entire surface and all the objects on that surface, and then you can use classifiers to say, okay, I have the roof of a building, or I have the canopy of a tree, and there's some very good algorithms to help you with that. So that's Canopo or any other automated point cloud classification algorithms. Randstad shape detection, that's an algorithm that will allow you to automatically detect geometrical primitives in your point cloud. It's not very useful in many, let's say, cultural heritage applications, but for example, if you're working in reversed engineering applications, where you have an object composed of very simple geometrical primitives, like a cylinder, a box, a sphere, a cone, or a torus, then you can use Randstad. Random consensus. I forgot the name of it, and now it annoys me that I don't remember the name. So let me go to where's voilà, here. Randstad. Random sample consensus. It will actually take a random series of points, and it will try to iteratively fit the best possible primitive on that sample. So it's an iterative process, and then you will end up with potentially with a large series of primitives using some geometrical constraints. But we will not use that in this summer school. Facets for geological modeling. Also possible shading, so some kind of omnidirectional hill shade. If you've seen hill shading in QGIS by Doc, that's also possible to do on a point cloud, and it will actually take a pseudo illumination parameter to enhance the visualization of your point cloud. Structure from motion data. So here it deals with bundler data. That's apparently an OUT output file, but it's also possible to use photoscan projects in Agisoft. So I will briefly demonstrate that. If I go to a sample that I have here, let me go. No. Let me go to this project, for example, and I will export it as save as, not as a PSX, but as a PSZ file. And I will just save it on my desktop. Continue. So this is the old school pre-Metashape project file that I just generated. If I go to that file, which is here, I can load it in CloudCompare. So let me make a new instance of CloudCompare. Voila, here it is. Then you can actually load your Agisoft. Allez, typical. Because of the fact that it's on the wrong location, I hope. Put it here. Last attempt. So under normal circumstances, I have no idea why it's not working at the moment, but it is possible to load Metashape projects and to have a look on the orientation of your original photos, see the relation between your photos and your dense point cloud, incorporate your 3D model of it, and it will help you to get a better understanding of the geometry of your different features. And then last but not least, the ability to work with sensors. So I briefly showed it when I was visualizing my terrestrial laser scan data. It is possible to make some kind of a virtual copy of your laser scanner, give it coordinates. That's what you will find here, for example. You say edits, sensors, TLS create, then you can press it here, set a location, and it will automatically calculate a depth map, so the distance from each and every point in the point cloud to the scanner that you define here in this screen with an X, Y, and Z coordinates and transformation and translation coordinates. And you can use that for also for filtering purposes. So points that are further away than a certain direction or outside the scope of the sensor. But also this is something that is possible. So please be aware of the fact that it is available and that it's working, and it can be very useful. But we will not cover that in this specialist course unless you explicitly ask me for a demonstration on it. And then for full information, the ability to have some other options. So you can make animations. I have no experience with that, but it is possible to make point cloud animations or 3D animations in CloudCompare. Work with hidden point removal. So if you have a point cloud, especially point clouds that have a normal direction, you can use hidden point removal to make visualizations where all the points that are pointing away from your direction, from your viewpoint, are eliminated. So it will give you a better impression of the points. Poisson surface reconstruction, simplified 3D, simplified way of making 3D meshes, full 3D meshes of surfaces. Surface revolution analysis. I've now experienced with that. So that's actually what I wanted to show you in CloudCompare. While we are still here, I will go to the Moodle platform. So let me log in, and I will open the thing, the session about CloudCompare. So that is now open. Highlights. Open, show topic. And here you will find a task, the task that refers to the point cloud that you will find on the web server as well. So this point cloud has been generated last year during the summer school of the site of Daphne, the monastery Daphne near Athens. I took my camera, I took a lot of pictures of this site, so this is just terrestrial photogrammetry. But the result of this process is a very dense point cloud. And let's assume that this point cloud is derived from laser scanning. So officially, I will tell you now, it's not from laser scanning, but let's assume that it's from laser scanning. If you download that data set and you open it in CloudCompare, you will see that the orientation is totally wrong, absolutely totally wrong. So the first thing you will have to do here is level your point cloud. So you can use the leveling tool by clicking on 3 points in this area, and that will automatically level the point cloud. I will also ask you to make a subsample of that point cloud with a minimum distance of 1 centimeter. Be careful that if you take the point cloud and you just press 1, that you will have a subsample of 1 meter. So you will have to consider the correct units in that case. I will ask you to generate several cross sections. So use the cross section tool, as I've seen, as we have seen here, cross sections. So try to familiarize yourself with that function. Make a clip of the area. So the area that is here indicated with a red rectangle, and then try to calculate the best fitting plane via tools, and then tools fit plane. Refine the clip and make sure that you have enough ground level points. So please don't make it too small, but also make sure that you don't have points of the walls included in it. And then if you have this plane, I would like to ask you to calculate the distance from the original point clouds within the red area to that plane, and that will give you an indication of the micro topographical variations that are available in this point cloud. And then, just as a finishing touch, I would like to ask you to generate some geometric parameters out of it. So, just as a reminder, I click away from this screen, you go to Tools, Tools, Other, Compute Geometric Features, and then try to understand or try to derive some of the parameters that you have here. So point density is something that we have seen. We have seen the curvature, so the convex and concave shapes of your topography. Roughness is something that you can do. And please also have a look on this list, some different features. If you're not familiar with eigenvector calculations or principal component analysis, please don't calculate it, because it's something that's very useful for geometrical analysis. But if you have no idea what principal component analysis is, then I don't think it's very useful to test it. But the other parameters, like verticality, if a surface is pointing upward, or if it's like this or this, I think these are quite interesting values that don't require too much statistical background. The thing that I will ask you here is not to upload your resulting point cloud, but just try to make some screenshots showing the work that you have been doing on the point cloud, and then you can upload it here in this task. Voila. That's what I wanted to show you. I really hope that you that we can share this this enthusiasm for this software after doing these tasks. And I hope that my my introduction to the software was clear. That also the demonstration that I gave with multiple point cloud was also clear. Of course, it was very short. Normally, I would guide you through the software step by step, but it's not very convenient, of course, in this configuration. But I hope that you you can familiarize yourself with the software, that you find this task very useful, and that you will find the software in general very very useful for the rest of the exercises. The reason I give you a very broad task here is that we will use CloudCompare for these 3 sessions. So registration, filtering, and deliverables. We will use CloudCompare to work on these sessions, and then the last session is on the generation of something like this. So you will make your own 3D visualization of your own object using using this software, but that's for the last session. Voila. Do you have questions?